Hey guys, this is Professor Janacek, and I would like to explain to you how to find potential functions of conservative vector fields. To begin with, our conservative vector field, uppercase F, I will describe as made up of the components f, g, and h. Our potential function, if you remember the definition, I'll call phi, and the definition of a potential function means that the first partial with respect to x of phi is going to equal to f. The first partial with respect to y will equal to g, and the first partial with respect to z will be equal to h. So the potential function, if I take the first partial derivative with respect to x, I get the first component of f. If I take the first partial with respect to y, I get the second component. And if I take the first partial with respect to z, I get the third component. That's the idea of a potential function. Well, if we have that the first partial with respect to first partial with respect to x is equal to f, then I know that if I integrate with respect to x, I would have to I simply integrate f with respect to x. Similarly, I could integrate g with respect to y, or I could integrate h with respect to z. Any one of these would give me a value for phi, right? Integrating a derivative gives you that function back. So phi would be equal to the integral of f dx, but notice there would be a constant, and that constant could possibly have a y and a z. It's a constant with respect to x, not with respect to y and z. I could also find phi by integrating g with respect to y, but the arbitrary constant in the back might have x's and z's. And finally, in order to find phi, I could integrate h with respect to z, but then my arbitrary constant could have x's and y's in it. So let's go through this whole process and see how to find potential function. Let's start with the conservative vector field described by e to the x cosine y and negative e to the x sine y. So I'll begin by letting lowercase f be the first component, e to the x cosine y, and g being the second component, negative e to the x sine y. Well then, again, according to the definition, the first partial derivative with respect to x of phi has to be equal to f. And the first partial of phi with respect to y has to be equal to g. Right? Again, that's the definition of the potential function. Well, whoa, where'd that go? All right, there we are. Thus, if I wanted to integrate, if I integrated one side, I'd have to integrate the other. Oops, I want to integrate with respect to x. Actually, let me go ahead and write it this way. My goodness, there we go. If I wanted to find phi, I would integrate the first partial with respect to x. The first partial with respect to x, I integrate with respect to x, right? So that would give me the integral of e to the x cosine y dx. But what do we get? Now, obviously, I could have also integrated with respect to y and used this other one, but I'm just going with that first one. Thus, we have that phi is equal to, again, all I'm going to do is integrate with respect to x. I just need to integrate that with respect to x. That's going to give me e to the x, oops, e to the x cosine y plus a constant, but notice I just integrated with respect to x, so this constant could potentially have a y value in it. All right, now I've only used the fact that the first partial with respect to x has to equal to f. That allowed me to set up that integral, right? I have not used that the first partial with respect to y is equal to g. That's what I'm going to use now. Notice I now have a phi. Oops. I now have phi, and so if I take the first partial of phi with respect to y, again, I'm looking at this guy here, taking the, I know that's going to be equal to that. I'm going to just, what is the partial? I've got a definition for phi. What is the first partial with respect to y? And then notice I'm differentiating with respect to y now. That's going to be negative e to the x sine y plus the derivative of c, which has y's in it, is going to simply be c prime. But remember, I know that this has to be equal to negative e to the x sine y. Well, looking at these two, setting these two guys equal to one another, I see that c prime must be equal to 0. Well, if c prime is 0, then what is c of y? Well, that's equal to some constant. So I will choose c naught to be equal any constant. I'll choose 0. Therefore, our potential function phi which, by the way, is a function of x and y, and I have its definition right here. Phi, there it is right there, is equal to e to the x cosine y plus c e to the x cosine y plus c, but c, remember c we said is c naught, but c naught we said is 0, so that would be simply plus 0, but we don't need to write plus 0, so there we go. Our potential function is e to the x cosine y. I do want to let you know that we could have approached this a different way. I could have started with integrating the partial with respect to y, integrating that with respect to y, and then I would have actually had to then taken the derivative of that with respect to x. So notice we integrate with respect to one variable, and then we differentiate with respect to the other. Let's take a look at another example. Here we have a vector valued function f. This one has 3 components. So the first thing we'll do, we'll let lowercase f be the first component. We'll let g be the second component. And we'll let h be the third component. Notice these are all 3 functions in terms of x, y, and z. All right, this tells us that for our potential function phi, the first partial with respect to x must equal to x, the first partial with respect to y must equal to g. And the first partial with respect to z is equal to h. Right? That's our definition of a potential function. All right, so now all I want to do is I want to either integrate this first piece with respect to x, or integrate the second piece with respect to y, or I'll integrate the third piece with respect to z. You know what? I'm kind of liking that one. Now, again, you could pick any one that you want. I'm going to go ahead and work with that third piece. So I am going to integrate the first partial of phi with respect to z. I'm going to integrate that with respect to z. Okay, well, when I integrate phi, the first partial of phi, I'm integrating a derivative, that just gives me phi. All right, on the right-hand side of this, again, I'm integrating, don't differentiate, I'm integrating with respect to z, we get y squared e to the z minus 3xz, oh, no, that's going to be a 2x z cubed plus my constant. My constant I'll call it my first constant, C1, could have x's and y's. Because I integrated with respect to z. I know it's not going to have a z in it, but it could have an x or a y. All right, so I've used this fact right here, that the first partial of my potential function with respect to z is equal to h. Now let's go ahead and let's use the fact that the first partial with respect to x is equal to f. That means if I take the first partial of this with respect to x now, I'm going to take the first partial with respect to x. That gives us, notice this first term has no x's, all right? Second term, with respect to x, I just get negative 2z cubed plus, taking the derivative of this with respect to x, I get, actually, you know what, I'm going to back up. I've realized that that's maybe not a good choice here. Let me just call that, oh, what do I want to call that? Oh, well, we'll just go with that C1. I'll call it now, so when I take the first partial, I'm taking the partial with respect to x, so I'll call it C1x prime. But it could still have x's and y's. But remember that this partial has to be equal to 2x cosine y minus 2z cubed. Well, if I compare these two, the left side of that equation and the right side of that equation, I realize that c sub 1x prime has to be equal to 2x cosine y. Well, then what is C1x? Notice I'm going to integrate with respect to x's. Notice I'm integrating with respect to x. This gives me x squared cosine y plus a constant, call that C2, but this constant is going to be in terms of y's only. Notice my C only has x's and y's in it, right? I just integrated with respect to x, so I'm not going to have any x's, but it might have a y, so this is now just a function. Actually, I'll just call it C2. This will be a function just of y. All right, so now if I look at phi, it's y squared e to the z. All I'm doing, by the way, is following this right here. Y squared e to the z minus 2xz cubed plus this c1, which, by the way, is really what I have here. This is just a c1. But c1 I know is x squared cosine y plus c2, just a function of y. Whew, all right, well, let's see now. I'm going to use the fact that the first partial of this has to be equal to g. First partial with respect to y. All I'm going to do is take the first partial with respect to y of this. That gives us two y e to the z. Second term is 0, doesn't have any y's, minus x squared sine y plus c2 prime. But we know that that has to be equal to g. So that is equal to 3 plus 2y e to the z minus x squared sine y. Looking at the two sides of this equation here, I can see that c2 prime must be equal to 3. Well, then what is C2? If I integrate, again, just with respect to y, notice this is only a function in y. If I integrate with respect to y, I get 3y plus yet another constant. This time, though, I will choose that constant. Oh, that's supposed to be a C3, my third constant here. I will choose C3 to be equal to 0. Hence, we have phi. All I'm doing now is kind of filling in the blanks of what I have here. Phi is equal to y squared e to the z minus 2xz cubed plus x squared cosine y plus c2. Remember, c2 is equal to 3y plus c3. Plus c3, but we chose c3 to be 0 because c3 is a constant, an arbitrary constant not dependent of any variable. I can pick 0, but I don't need to write that on there. Therefore, we have found our potential function. Whew, my goodness. Wasn't that something? Well, enjoy.